Welcome back to the course. We took a break. I want to deal with the topic of continue with electrical conduction in solids. What we had looked at was what is called the Drude's theory of electrical conduction in solids. That's what we had started. And our basic idea was to define what is J, which is current density, and we had defined it in terms of a charge per unit area per unit time. Right? We had called that the flux of charge that is flowing through. And then we were looking for a relationship between J and how does that relate to, or J's relationship with the applied field. This is what we are looking for. And as part of that, we went through the derivation that J was equal to E, N, and a drift velocity in the x direction. So we wanted to find the relationship then between this drift velocity and the applied field. And having looked through a mechanism whereby the electron would start with some velocity, accelerate, and then get scattered, and so on this way, we ended up relating V to Ex as V dx is equal to E tau by ME, and then Ex, the applied field, right? So this allowed us then to go on to define a mobility, which we call drift mobility. And then what we did was to write J in terms of all this as E, N, mu d. Okay? This is where I think we ended up simply by substituting for this as sigma, giving us another variation of Ohm's law. This is where we left off. Well, we'll take it up again from there. What would be the temperature dependence of this conduction mechanism? If this is how electrons behave, that they're passing through a metal, they accelerate, and there is periodically they're getting scattered, then what would be the temperature dependence of such a mechanism? That's what we'll deal with today. Okay. And what we'll treat first is the ideal case of pure metals. There are no impurities, and so the scattering is going to take place primarily by phonons, the atomic vibrations that are there. So that's what we'll treat first using this model and try to derive a temperature dependence for it. And then what we will do is to look at what would happen if there are other additional impurities or defects in the material, and how does that modify the temperature dependence. So primarily we will define then that the temperature dependent conductivity is defined as sigma T and the corresponding resistivity as rho T. So these are temperature dependent terms. Now for every scattering center, which in this case we are restricting to just the atomic vibrations, there is something that we will define called a scattering cross section. Okay? And fundamentally it simply means an area of influence, if you want to understand it in very simple terms. Atoms are vibrating around a mean position, and how close does the electron have to get before it feels the influence of this vibrating atom? That's what we mean fundamentally by the cross section of an atom. Now, since the atom is going to vibrate in all directions, we'll get something like this. And in a simplification, we can define an area S, which is given by pi a squared. All right? A is that radius there of vibration. So as long as the electron and its passage through the material comes within this area around that vibrating atom, it's going to get scattered. And so the electron has got a certain velocity, defined earlier as u, and when it comes within this area of S, it's going to get scattered. Now earlier we said tau is the time between collisions, the mean scattering time, right? So from this we can define something called a mean free path. The time between collisions is tau, the velocity of the electron is u, so the mean free path L is simply u tau, velocity times the time between scattering. Given that there are ns scattering centers per unit volume, this is the concentration of scattering centers. Excuse me. All right, we are giving that this is what the value is. Now I know that in this time interval tau, it is not undergoing any scattering. All right, so when it passes through that length L, and we are talking of an area that is given by S. So if we have two scattering centers, something like this, and this is then the value L. Right? It got scattered, then it doesn't get scattered till it gets to the end of L on an average. So what we can then say is that ns times the volume. Okay, this is the concentration, number of scattering centers per unit volume, times the volume. Volume in this case going to be given to us by area times the distance. It's the volume of the cylinder. You follow that? So the electron got scattered here. It's going to travel for a distance L before it gets scattered again. That's what we mean by the mean free path that I just defined as u tau. It's not going to undergo scattering till it gets on an average past L. This is, remember, it's an averaged out value. So ns is the concentration of scattering centers which is per unit volume. So when I multiply ns by the volume, there's no scattering center in between. The next one will be on an average somewhere here. So we get that ns times this is just 1. There's one scattering center on an average within this volume. All right? Are you with me? There is ns is the concentration of scattering centers per unit volume. The volume that it is traversing on an average before it gets scattered again is area times the length there, the mean free path. And so we have only one scattering event in this volume. Okay? And then we can substitute here for L and write it as ns times S u tau is equal to 1. I simply substituted for L there. When we do this and rearrange for tau, I will get a term u ns. So what I'm interested in is the temperature dependence of resistivity. Where am I going with this? Since the primary thing I want to know is how does this tau, the mean scattering time, change with temperature. If I can figure that out, its temperature dependence, then I can figure out the temperature dependence of the resistivity term. So that's what I'm going to look at. Now ns is, does it have a temperature dependence?
Yeah.
The number of scattering centers per unit volume, does it have a temperature dependence? Imagine, remember, this is a pure material with no defects. So at a first approximation at least, there's no temperature dependence to ns. We can take that to be approximately the number of atoms per unit volume. Because fundamentally the scattering is coming from the atoms, so the concentration of scattering centers is nothing but the atomic concentration that we have. All right? But remember, we talked of vacancy production and things like that. As you go to higher temperatures, there are vacancies that are formed. Intrinsic. I'm not introducing any other defects. Right? But we are ignoring that. We are not talking of a huge temperature range at this point where that can play a significant role. We're just talking of a very simple idea. So ns has got no temperature dependence. Yes?
As we increase the temperature, the region of scattering increases.
Which is related to S, not to ns.
But then the volume that we cover, in that the number of scattering points would be less because the area is
Not as significant. That's why I said there are temperature dependent, but we can ignore it. All right. The significant change will come from the change in S, which is what is related to as the temperature increases.
N is related to S in some way.
Yeah. But again, overall, when you look at a volume of material, that change is very, very insignificant. On an average, it is related to the expansion of the material. That's what you're trying to say, right? I increase the temperature, the total volume therefore increases effectively. We saw earlier how that is done, and therefore there's only same number of atoms over a larger volume. But that change is relatively insignificant here. But that's why I said it's an approximation that allows us to say they're roughly constant. Remember, we are talking of a theory that was formulated many, many years ago, Drude's theory, as an approximation to try to understand what is happening in metals, to start with. And then various additional ideas were introduced subsequently, which we will do, including quantum ideas, to understand the overall behavior in all kinds of materials. But at this point, it's simply dealing with some simple ideas. Can we explain the observed temperature dependence? Because I can measure the temperature dependence of resistivity in a real metal. So what we are trying to do is to see if atomically speaking or microscopically speaking, we can derive some ideas, simple ideas that will allow us to explain that phenomenon. All right? So Ns we are holding has got no temperature dependence. The other thing would be, what about the velocity u of the electron? Will that have a temperature dependence? The answer is yes, but it's not going to be as if it is like a gas. Kinetic theory of gases gives us how the velocity of atoms that are, flying around inside a container, it's a gas, so there's very few atoms. We can derive that from kinetic theory, something like half mu squared, which is the velocity, the energy, kinetic energy, is equal to 3 by 2 kT, right? You know this from earlier classes and things like that you've taken. So the kinetic energy is equal to the temperature dependent term here. So I can rearrange this and get something like u is proportional to square root of T. Now that is if electrons behave like very weak dilute gases. But in reality, electrons don't follow kinetic theory. We will come to that. They follow what is known as Fermi-Dirac statistics. So they are not following Boltzmann's equation and things like that in general, but we are going to use later Fermi-Dirac statistics to understand what is happening with electrons. They follow a different kind of mechanism. And it turns out that U does not have a square root of T dependence, but rather a weak temperature dependence. Okay, rather weak temperature dependence that we get from Fermi-Dirac statistics. So this term also more or less we are holding it, does not change very much. Ns we have approximated, that is also not changing. So fundamentally then the question is, how does S change with temperature? Scattering is occurring from an area S. So now we want to know, how does this change? We can assume that temperature is inversely proportional to area. It would be a logical thing. The scattering time, mean free time. As the area of the scattering increases, the chances that it will get scattered are more frequent, and therefore the mean free time is then inversely proportional to the area, right? So tau proportional to 1 by area, which we can write as tau proportional to 1 by pi a squared, which is the area of my scattering center. And A is simply the amplitude of vibration. Now, these atoms are behaving like springs. So we can use ideas from simple harmonic motion to try to understand how these atoms are vibrating. Okay? The average kinetic, so they are behaving as if like tied to a spring, and then they vibrate back and forth. That's the approximation we are making for the atomic vibrations. So the average atomic kinetic energy, not electrons, but for the atom, is given by what? Atoms vibrating with kinetic, what is their kinetic energy? In simple terms, what will it be? Half mv squared, some velocity term squared, right? So we will write that as half the mass of the atom, and then we will write that the velocity is given by a omega. There is a no, just an a omega term. a radial frequency, right?
We are assuming it as
Because it is in simple harmonic motion, back and forth, right? So V in this half mv squared term is the radius times omega. So what we get there is a squared omega squared, where omega is equal to 2 pi f, the frequency of vibration for simple harmonic motion. Okay? So I've got this term as the average kinetic energy, which I can then relate to temperature through 1/4 m a squared omega squared is approximately equal to half kT. Okay, these are all, I'm not interested in the exact numbers, whether it's 3/2 kT, half kT, that's not really, we're looking at an overall temperature dependence. From which what will we get? That a squared is proportional to T. Right, the exact proportionality constant being different. Now go back and see, we saw that tau was proportional to 1 by pi a squared. So what do I end up getting? Tau is proportional to 1 by T, because tau was proportional to 1 by pi a squared, and a squared is proportional to T. Okay? This we can write then as tau is equal to some constant times T, where C is a constant. So these are all very, very simplified ideas coming down. And now I can go back. I know that my mobility term was what? E tau by mass of the electron. So I'm going to make this substitution for tau here to look at what is the temperature dependence of my mobility. And when we do that, we get that mobility is equal to E C by T me, substituting for tau in there. All right? So now I have a temperature dependence for mobility. Sigma T then becomes equal to N E mu D. So we can write that as N E squared C by M E T. Right? So in other words, we've got that sigma T is inversely proportional to the temperature. As the temperature increases, the conductivity decreases, or rho T proportional to T, since rho is the resistivity. So for rho T also we can then write the expression, since it's equal to 1 by sigma T, as simply the inverse of this. Okay? So we have some simple expression that relates for an ideal metal, pure, the scattering is simply due to the vibration of atoms. Rho T we will expect proportional to temperature, or sigma T proportional to 1 by T. We can write that as rho T equal to some constant times temperature. So if we plot this, what are we going to get? Rho T versus T, a straight line with a slope A. As temperature increases, resistivity increases. All right? This is where we have assumed this is a pure metal, nothing else is happening. And what do we see at low temperatures? What should the resistivity then be according to this idea? Right? But reality, when you plot, looks a little different. And that's because reality is not an ideal metal with only scattering due to atoms. So let's take the case of impure metals. Where in this case we are introducing, in addition to the atomic scattering, we have impurity scattering too. Okay? So there's the atomic scattering is still there, but we've added on one more term, and impurity scattering. The impurity atom that we are putting in there could be larger or smaller than the host atom. We saw that when we were talking of defects. Right? And therefore, it will introduce a strain field. So when we put in an impurity into a host lattice, depending on whether it is larger or smaller, there will be a strain field around the impurity. And it is the interaction between this strain field and the passing electron that causes the additional scattering. Okay? Electron scatters from the strain field. So the atoms of the host lattice themselves vibrating produce scattering, which we saw has got a temperature dependence rho proportional to T. In addition, now we have scattering from the strain field that is related to the impurities. So we have two scattering times, one that is temperature dependent, which we saw earlier, and now we have another one that is impurity dependent. And we have to see how these add up in the material, how we may look at the temperature dependence of this, if there is any temperature dependence. And these two are events that are occurring independent of each other. Okay, just because there's no relationship fundamentally between when it last scattered, whether it was an impurity atom or a host atom, they are independent events. Okay, so both of these can occur independently. That is important when we look at the statistics of it. Basically, if tau is the mean time to scattering, 1 by tau is what is a probability of scattering. Okay? And because these are two independent events of scattering, from statistics we can show that for these two independent events, the total tau is given by 1 by tau is equal to 1 by tau t plus 1 by tau I. Since they are not linked to each other, statistically this is what will come. The total scattering, that is we see in the material, is given by 1 by tau is equal to 1 by tau t plus 1 by tau I, the two scattering times. Okay? Now tau that we have here will always be less than tau t or tau I. It's obvious from that equation, right? That this tau, the overall scattering time, will be less than tau t or tau I. What does that mean? That now my mean free time with these two events there, one coming from atoms and one coming from impurities, is lower. In presence of impurities. Right? So I've got that tau is related in this fashion, and then we can look how mu relates to tau. Mu is proportional to tau from earlier equations we know. So I can then simply write 1 by mu is equal to 1 by mu L, mu t plus 1 by mu I. Since mu is simply proportional to tau, okay, the rest of it is constants there. Mu t plus mu I. One that is due to temperature dependent mobility, one that is due to impurity dependent mobility. And each of these, mu t was given to us then by E tau t by me, and mu I was given to us by Ti by me. Okay? You follow that progression, right? We have gone to, the taus are related to each other in this fashion, and since mu is simply proportional to tau, we can substitute then in terms of mu. So now since I know that rho, the resistivity, 1 by sigma, is given by what? 1 by Ne mu. We are using the subscript d to indicate it's a drift mobility. That's how we had, it's drifting in response to the field. So that's what's called a drift mobility, as opposed to, we'll see another term later. So we have rho is proportional to 1 by this. So now what can I write? My rho term, making the substitutions then, is equal to 1 by Ne mu t plus 1 by Ne mu I. Okay? I just simply substituted where I have for 1 by mu, we will get this equation. What is that? What is this term? Rho t, very good. And what is this term? What we can call as rho I. So it turns out when these two scattering mechanisms are independent of each other, the temperature dependent scattering and the impurity dependent scattering, what have we got? That you simply add up each of the resistivities. In terms of resistivity, they simply add up. And this rule is known as Mathiessen's rule. It's a very useful rule. Okay? That if I have two mechanisms, the resistivity is simply the sum of the resistivities independently taken for each of these mechanisms. Now I can extend this idea even further. We talked of impurity atom. What if the scattering is not from an impurity atom but from a defect? Say a dislocation or something like that. They also contribute to the scattering. So in that case, what will happen? I've got now that my rho total is equal to rho t plus rho impurity plus, let's call it a rho defect. In other words, simply because my scattering time has become a sum of these. This is the important one to remember, that because the scattering time is related this way, I get this consequence. So no matter how many scattering mechanisms we may postulate in the system, Mathiessen's rule allows me to say, okay, there's all these scattering mechanisms, but the sum resistivity that I observe in the material is nothing but the arithmetic addition of the different resistivities. So that's very convenient. Now when we plot something like this, what will we expect? Well, there's multiple things. Okay, first of all, I can club these two and call that simply residual resistivity. Okay, rho r referring to a residual resistivity. We will see why that name comes. Residue. What's the temperature dependence of impurity scattering and defect scattering? They are relatively, again, independent of temperature. So now I have a mechanism that looks, it's got some value like this. Then I plot rho versus t. Okay? That's, let me just call that rho r, the defect related scatterings. And I've got a term that looks like this, which is my temperature dependent phonon scattering. So what will I expect of the overall resistivity in a material in which both these kinds are there? Mathiessen's rule says that I simply add up these, right? So at this point, what will be the resistivity? This plus this. So right there. Then it goes somewhat like this, and then what? Then we expect it to go something like this. Something like this. It's not exact, but of that nature. So I have two mechanisms, a residual resistivity term that is temperature independent, and I have a term that is rho t is equal to A times temperature. So the overall resistivity in this case is the sum of these two terms.
So it should be a straight line.
What about here?
Yeah, if you are adding both lines, means rho r and rho t.
Yeah, I'm saying there is actually another. We'll see that this is not strictly true. There is another temperature dependence. Okay? It is an addition of these two, but really at low temperatures it doesn't behave like this. So this part here is strictly speaking not true. Some of this, it doesn't extrapolate that way. We'll come to that. Okay. But effectively, above a certain temperature, the temperature dependent scattering due to phonon scattering is the predominant mechanism. And the mechanism due to impurity scattering is rather small contribution to it. And that's why initially, that is at low temperatures, we see that is the effect is primarily due to impurity scattering. And then as we go beyond some temperature, the phonon scattering takes over. So what we observe in reality is something like this. Remember, we made so many approximations. We can't expect it to actually match A. If it matches, that's great. So this guy was working with all these ideas, and he has made many approximations to give us a simple picture, just simply based on scattering from vibrations and atoms like that, and using a mean free time idea and so on. All right, there's plenty of approximations in here. So this is what is the expected behavior of rho for a metal that has got impurities in it. And now you can see why this is called residual impurity. In other words, no matter how low a temperature I go to, I will always have some resistivity term. Now, depending on the particular metal, this term could be very, very low, almost unmeasurable. Okay? Because if you have very, very pure metals, then this will be low. Very pure and very perfect, because that is just due to defects. So if I can reduce the defects in my material, if I can remove the impurities from my material, this term proportionately will keep coming down, lower and lower. And so what I will see may be some term like this, right? So depending on the purity, there will be change. The other thing also, since it's defect related, what will be the influence of mechanical deformation? Purity I reduce, I can expect, okay, there are fewer scattering centers because there are fewer impurities in the material. But what about when I introduce deformation? How will that affect it? We will increase the resistivity. Why?
Because mechanical deformation will increase the defects.
What kind of defects typically? Dislocations and things like that. So the more we deform, say cold working of a metal and so on, and then we measure. So I took a metal piece, I measured its resistivity versus temperature behavior, and then I cold worked it. I did all kinds of, rolled it, deformed it in various ways, and then I took its resistivity again. So I will expect to see a higher resistivity simply because the number of dislocations that have been introduced into it increases the rho r term. So mechanical deformation also increases my resistivity. Okay? So if I have materials which have not been annealed out maybe, and you've annealed out a lot of the dislocations, again the resistivity will come down. So now this expression that we have, the new will be something like AT contribution from the temperature dependent scattering plus B, a temperature independent term. So that no matter how low I go, I'm always left with a term B, which is my residual scattering. So in real metals which have got impurities in it, we expect that it will follow this kind of a behavior. Rho is equal to AT plus B behavior, which is basically what this equation is. There's a temperature dependent term whose slope is A, and then we've got a B term which is related to the residual. We can then talk in terms of a temperature coefficient of resistivity, or TCR. Temperature coefficient of resistivity. In other words, how does the resistivity change with temperature? All right. We define alpha naught, which is the temperature coefficient of resistivity, as the change in resistivity per unit temperature change at a specified temperature T naught divided by the original resistor. Okay, the fractional change in resistivity with respect to a reference temperature T naught. So at T naught, the resistivity is rho naught. How does it change when I change the temperature? And these the reference temperature that it is typically defined at is of the order of either room temperature, or 0 degree centigrade, or of room temperature. Very often you have to specify that temperature. Okay, so they'll give some reference like this. Now when you look at this equation here that we have, alpha naught is equal to delta rho by delta T, if the rho behavior is modeled by this term, then what we get is that alpha naught is constant within a certain range of temperature. It's a linear dependence, right? So we can write this term then, alpha naught, as rho minus rho naught by T minus T naught divided by, okay, same definition. We are having a constant term. If it is something that goes on changing in different regions, then we use the differential there. But since in a certain range, and if it's following this rho is equal to AT plus B, we can express it in this form, which can then be rearranged to give us rho is equal to rho naught 1 plus alpha naught T minus T naught. What does this remind you of? Thermal expansion coefficient, right? It's very similar to that, this equation. That if you change, if you had substituted length here, L is equal to L naught, and instead of the TCR, this was the thermal coefficient of expansion TCE, then you would have got a similar equation. So rho is equal to, this is the more familiar form of the same equation that we have here, the temperature coefficient of resistivity. Be careful, remember now that my alpha naught is defined for a specific temperature, okay? There is a T naught, rho naught dependence on T naught. So when I'm defining my alpha naught, it is dependent on at what temperature I'm talking about, because this rho naught term itself depends on temperature. So that is why we talk of thermal coefficient of resistance, temperature coefficient of resistance at a particular temperature. We define it at that temperature. Okay? Now we can make some more refinements to these ideas that we've been talking about. What we did was we said rho is proportional to T. There is a AT plus B. And so what we expect is something like this, a linear dependence, and the lower temperature, the residual part of it, when we plot rho versus T. What happens when we look at real data? What do we see? Something like silver, copper, which are very good conductors. You may see for silver, copper, and so on. Okay? So this is my model, and we find that it's got a pretty good fit. That's the model. Silver and copper have a pretty decent fit, similar slope. When we look at some other materials, for example, tungsten, I'm just giving you a representative idea. These are nothing like any exact values. That's also not bad. Okay? But when we start looking at something like nichrome, what is nichrome? Nickel chromium alloy, right? And it is often used in heating elements. You can see why. The resistance does not change much with temperature. It's got a very flat temperature coefficient of resistance, which is what you're looking for in many ways, because as you heat up the material, the amount of current it will draw will drastically change for some of these kind of materials, and you'll have to have other kinds of electronics to control that. But with nichrome wire, you're not changing that very much, because the resistance is remaining flat, relatively flat. Here's another interesting one, nickel. Does not follow theory, right? Yeah, this is my theory. Nickel looks like a bent elbow there. And then there's others that are also there. Monel, another alloy. Another, what is that? Yeah. What we see is that in the case of monel, nichrome, this one was for nickel, they are magnetically, the elements that are there have magnetic properties. Nickel, for example. So when the electron is moving through a material that has got elements that exhibit magnetism, not only is the scattering and interaction taking place as in the regular case, but there is a magnetic interaction with the electrons too. Remember, an electron that is moving in a magnetic field experiences a deflection. We'll see that in a second. Electron, there's a wire, current flowing through it. You place it in a magnetic field. That is the whole basis of our motor. It will experience a motion because the wire will move. There's a force that the electron feels in the magnetic field. So when the elements that are involved here exhibit magnetism, then it does not match very well with our Drude theory. Okay? That is one of the reasons why, because we haven't included anything of magnetism in Drude theory. All we're taking is impurity scattering and atomic vibration scattering. The other thing with nichrome, for example, is that there is impurity content domination. Mostly it is dominated by impurity content. Remember, for nichrome, we saw that the resistivity dependence of the residual part is temperature independent. I'm sorry, the temperature dependence is not there for an impurity dependent term, right? Where was that? This part here. But let's say throughout the alloy, the impurity part dominates. There's so much of scattering coming due to impurity or defect. Then we will expect that instead of doing this, it will follow more or less a flat profile. And that's what we see in the case of nichrome. There's alloy scattering, which I will not go into great detail. In different areas of the alloy, we'll get scattering due to the mixture of nickel and chromium. Okay, it goes on changing there. Nickel atoms and chromium atoms are in there. So the impurity content, if you want to think of it as chromium inside nickel, is the one that is going to predominate over the temperature-dependent vibrational scattering. So those are some examples that show that while we looked at Drude theory, the simple conduction model, it is only an approximation. It doesn't give us, for simple metals like silver, copper, tungsten, and so on, it's great. It explains the behavior of the temperature dependence. But when we start introducing other things like magnetic behavior and things like that, we no longer have the ability to express it by a simple theory like this. Another approximation to explain reality is what is called the power law approximation. Power law approximation. Rho by rho naught is equal to T by T naught raised to the power n, where n is an exponent. In the ideal case, n is equal to 1. So it simply goes back to the old idea. If n is 1, rho is equal to T by T naught. It's just a linear dependence, right? So for pure metals, like that silver and copper, the exponent is 1. This is simply an empirical law, something to explain the observations. There is no theoretical basis for writing it this way. And then when n is maybe 2, this is a better one that explains the one for scattering with magnetic interaction. So we've taken the existing data and modeled it and said this is what's called the power law dependence. When for pure metals, n is 1. For those where there is magnetic interaction, n is something like 2. One further refinement we can make is, I told you that the extrapolation that we made to low temperatures was not strictly speaking very true, right? Somewhere down here we are running into problems. And when you look at real data at very low temperatures, what we had done was we said that the behavior looks something like this, but reality looks a little bit different. It will look somewhat like this. We are talking of a very low temperature regime. Okay, this whole thing is down maybe somewhere in this area. And we expand that out and look at the real data. It follows more or less a term like down here we have my residual resistivity, which is more or less temperature independent. But this region here does not follow the linear temperature dependence like this. The rest of it follows. Here rho is proportional to T. There's no problem. But there is a small section where actually rho is proportional to T raised to the power 5. A much more radical temperature dependence than the linear one that we expect from using the other theory. And this is due to the fact that at low temperatures, very low temperatures, the atomic vibrations are more rapidly quenched. So as we come to very low temperatures, the influence of the temperature on the atomic vibrational amplitudes is far more significant than at the higher temperatures. Did you get that? So here, every time the temperature changes slightly, there is a very significant effect, T to the power 5 effect, on the amplitude of vibrations, and therefore on the mean scattering time, and therefore on the mobility, and therefore on the resistivity. So in low temperatures, it doesn't follow that sort of nice linear profile anymore. We have a sharp change here. I'll take up scattering in other kinds of materials, and then time permitting we'll look at a phenomenon that's familiar to many of you, Hall effect. Using these similar ideas, simple mechanisms like this, we can deal with the conduction mechanism in semiconductors, for example. I'll be brief here in the interest of time. Silicon has a valency, for example, of 4. And so it is covalently bonded by sharing the electrons with 4 other electrons, with 4 other silicon atoms around it. So we can imagine it to be something of this nature, a network. Okay? Are you with me here? Was that a question? Okay, silicon has got these bonds. Now, remember, the atoms are vibrating with some energy. And it is possible that some of these bonds may get broken. Some atoms have more energy on an average than others, and so one of those vibrational motions could break one of these bonds. What do I end up with? There's only one bond there because it has broken, and an electron has been released into the system. The rest are all bonded with 2. Okay, I'm not extending it. But one of these bonds just broke, releasing a free electron. This free electron becomes one more conduction electron for me and can contribute to the conduction. But what has happened is that it has also left behind a region of net positive charge. All the valencies were satisfied. Now one electron has gone off. I'm having one positive charge there, net positive charge in a local region. It is this net positive charge that is left behind that is referred to as a hole. Okay? So we have electron that has been contributing to the conduction. We also have this net positive charge left behind, which we refer to as a hole. Will that contribute to the conduction? Yes. Because now this hole can move to this position here if this bond goes here. So what will that look like? I have satisfied this bond again, but instead I have moved the net positive charge in this direction. Okay? So the bond that was here, the electron that was here, went and made the bond there, satisfying this bond. So the positive charge moved from here to here. And this could happen in response to an applied field. So the field is such that the hole is moving in the direction of the field, and that is effectively as if the electron is moving opposite direction. The hole has moved from here to here, may go here, and so on. So now in my semiconductor, I have a different situation than the metal. I have this electron that I have freed up that can respond to the field. I also have a hole, or the absence of an electron, or a virtual positive charge that can respond to the field. So what does my conduction begin to look like? Sigma is equal to Ne mu E plus Pe mu H, where P is the number of holes, concentration, this is the number of electrons, because both now contribute to the conduction. So whereas previously we had sigma is equal to any mu, just only we are worried about electrons. Now I have to take into account the whole mobility, and that's the electron mobility as before, and the number of holes that are created. Okay? And there are different ways. In this case, we saw that one electron was freed up, created one hole. But I could do things to this semiconductor and affect the numbers, so I create holes and electrons in different ways. One was by temperature. I increase the temperature, more bonds break. So that is, temperature could help me. But every time I create the same number of electrons and holes, one electron is created, one hole is also created. But I could also effectively, artificially change that by what is called doping. I put in other kinds of materials in here and dope it. Or through defects. What kind of defects? Say, non-stoichiometry. I have a compound. Instead of having equal numbers, for example, stoichiometry, suppose I have gallium arsenide. I don't have, for a stoichiometric gallium arsenide compound, there's one atom of gallium and one atom of arsenic, all through. But let's say due to some processing problem or technique, I have fewer arsenic atoms, arsenic evaporated. Now I've got more gallium in there, resulting in a charge imbalance. Okay, that results in the formation of these kind of extra carriers. So in the case of semiconductors, we see that it has a behavior that is different from metals. We'll take this up further when we do the next class, where we'll talk of, say, Hall effect and how that looks different in metals and in semiconductors.